Yeah, good afternoon to all of you. It's a great pleasure to have the possibility to introduce Visplore a bit and maybe also bring in a bit of different perspectives to the topic of building using digital twins than you've heard so far. I will just open the share tray now and share my presentation with you. So, can you see my slide?
Yes.
Okay, excellent. So maybe start a bit by saying a few words about our own background. What is Visplore? We are a software company, and basically our goal is to enable also non-data scientists to work very efficiently with massive process data, especially from industrial applications. Our background is that this work is based on developments that we did in a competence center called Vis. And we are actually a spin-off company from this competence center that's now backed by a venture capital firm. And we are 12 people overall and located in Vienna, Austria. So this slide is just means to briefly illustrate that our customers mostly come from three broad sectors. One is industry with both continuous as well as discrete manufacturing processes. Then another focus is the energy sector, and as well as consulting and R&D, including actually some of the participants of today. Okay, now let's turn to digital twins. If you look at the life cycle of a digital twin, you can basically broadly distinguish four phases. You need to design it. Once you have it, you need to validate it. Then hopefully it goes into operation. And after some time, it will probably outdate and you need to refit it. And actually, each of these phases is very much about working with massive data. So for example, in the design phase, you typically need to understand and prepare historic data from a physical system. Yeah? For example, you need to distinguish relevant system states and you need to calibrate your models. In the validation phase, you might need to check if the outputs of your digital twin are plausible. Then, once it goes live, it will typically also generate data. And in many cases, one of the aspects is to also enable subject matter experts to use the forecasts, outputs of the digital twin in some way in their daily work. And sooner or later, the digital twin will become outdated. And so one of the tasks is that you need to constantly monitor if the digital twin is still reflecting the physical counterpart and eventually need to refit it based on learnings that you did. And in all these phases, preparing and working with analyzing massive data is actually where much of the effort, costs, and challenges of digital twin projects are in practice. So this is a bit related to kind of a saying in data science that the typical ratio in data science project is 80% of effort goes into data understanding, cleaning, integrating, preparing the data, and only the remaining 20% are actually the model building. So this might not directly translate to digital twins, which are more physically based in many cases. But nevertheless, still all this plays a big role, and we hear over and over again that it's actually can be quite a challenge. And this is actually where Visplore comes in. Visplore can support the digital twin lifecycle simply put by fast interactive analytics of massive time series data. So it's our goal to save time and make the analytics easily accessible. To this end, Visplore is structured as a set of tools for digital twin development and decision making. So this can include, for example, checking data plausibility, correlation analysis. We'll see a bit more in a few minutes. Next, Visplore is also designed for fast preparation of massive data, like, for example, labeling process states, cleaning outliers, etc. It includes some advanced analytics like pattern searches, feature selections, regression, and some more. And it directly integrates with some data sources, but also, for example, with APIs like Python, MATLAB, R, and some more. So I want to briefly make this a bit more concrete by means of two use cases. The first one's coming more from the aspect of building digital twins, the second more from using it. So in this case, it was building a physically plausible digital twin of a power plant. And the users were an Austrian expert consultant company developing digital twins of thermal power plants. The digital twin in this case was a physical process model that are refined utilizing historical data. And one of the biggest challenges is that this historical data actually doesn't cover all possible ambient conditions, and to allow the digital twin for extrapolating also formerly unknown ambient conditions. And regarding Visplore, goals of the consultants here was to support the selection of specific load conditions from historic data to actually ensure that representative data are considered over as much of the operating range of the power plant as possible. And this goes hand in hand with identifying implausible time ranges and to exclude them from the model tuning. And so how this can look like, let's start with the first step. Once you have historic data from the process, typically, we've also heard about things like that in other presentations today, it's about numerous time series, sometimes hundreds or even more. And reviewing them can be quite challenging. So the approach that we're taking here is not only to have the usual time series visualization as you see here at the bottom of this picture, but also to have some kind of overviews of many time series in this heat maps visualization on top. And how they relate to each other can maybe be explained here. In the overview, each time series corresponds to one row, like the one that is currently highlighted. And the color indicates periods of low values and high values. So, for example, when we highlight here some periods that match shutdowns with this blue overlays, you see that basically what you see up here by the color matches to what you see here down there by this time series plot. With a big advantage of being able to review dozens of time series at a glance and also see, for example, how they relate over time. So, for example, see do certain events happen at the same point of time or in some sequence? Are there some sudden changes? Are there missing parts of the data and much more? So after reviewing, the next key aspect is to label time ranges representing conditions, which then are needed for tuning the model. And this can look something like this. So selecting parts of the data and label them with meaningful labels. also with the ability to audit existing labels that might exist, for example, based on some background knowledge. And then once you have them, you can, for example, as I already said, directly switch to, for example, Python and feed your results there directly from Visplore. So this is how it's support to specify to label representative conditions. And the third step is to what they typically do is to look at correlations in order to do a plausibility checking of many different operation parameters, also those that are outputs of the digital twin. This can look something like this, that you have such overviews of correlations, and when you, for example, have two sensors correlating with each other, you can exclude outlying periods and reduce the correlations in a way like this. Okay, and what the consultancy company reports is that compared to how they did it before, they report savings of approximately 10,000 euro per project due to reduced effort for exploring and cleaning data, and also that they need now 20% less time for tuning the model, and overall that they get a significantly higher confidence in the historic data which they need for building their physically plausible digital twins. Okay, so much for the first use case of building how to support building digital twins. The second use case is from RHI Magnesita, which is the world leader in refractories. And the users there are engineers and subject matter experts. The digital twin there actually is no explicit model in this use case, but rather the process data that is stored in their historian, which is from OSIsoft Pi. But nevertheless, they refer to that as their digital twin because it basically captures all relevant process data from their processes. And the challenge in this case was to use that process data for asset optimization and being a bit more specific to extract and to compare hundreds of press strokes from this process data in order to analyze long-term changes of this machine behavior, and also to compare assets from different plants to support optimization, to learn, for example, how assets operated differently across plants, and to extract some guidelines from this. Okay, also looking at the approach, how they did this. What they basically did as a first step after getting the data here into Visplore is to use Visplore's pattern search tool for extracting machine cycles. So what you see here in this line below, press strokes with some time passing in between. So you see that they occur at irregular frequencies. And what they can do then is to select one of these strokes, simply search this pattern, and get 700 press strokes being visualized on top of each other, as you see on the top left side, which can then be used, for example, to select press strokes that form a certain cluster, and then again relate this back to the time axis on the view below and see when the pattern, for example, changed. So this is very helpful for extracting the strokes and seeing how they change over a longer period of time. Also to learn things like, for example, how do the machines wear or degrade regarding the performance, or how is the machine being operated by different users or for different types of products. And then, once they extracted the strokes for different plants, they were able to relate them using multiple views on the data. So in this case, it's actually in practice it were more than 2 plants. In this example, it's just 2 plants here that we see. And what we basically see is that one plant, shown in orange here, actually has longer durations of each of the machine cycles, but has some quality indicators being much closer to the set point, while the other was operated faster with the quality indicators being closer to tolerance limits. And also this basically is interactive. For example, you can hover over the plants in the visualization on top and, for example, get their corresponding data highlighted. So what's the result of this use case? What they learned for the first time is that by really comparing the asset data from different plants in a such detailed way is that they learned a lot about major differences in operation strategies, because actually the assets were identical. So it was just the way they were operated and parameterized, which were different, but the physical assets were the same. And this helped them to extract internal guidelines for asset operation based on these insights. And this in turn led to savings by learning how to save energy consumption for asset operation, as well as also insights related to quality. And very generally, and this is something that they appreciated a lot, is that using this interactive approach to data analysis, they were able to make this advanced analytics much more accessible to more subject matter experts, which then also used data for their decisions, and especially also complex process data, which they included for their decision making. I tried to just come up with just mention 3 more use cases where we see that it's a big benefit to include the human expert in the loop, because when talking about digital twins, a very common understanding is that this is something that's purely automated and used for some automated optimization, for example, or some automated monitoring, which is of course a very important use case, but there are also equally important use cases that actually require the human in the loop. And one of those is root cause analysis of process and quality problems. And this is a bit of a simplified example here, where you see that basically you have a problem in one time series characterized by these spikes here, and can identify other process signals where we basically see things like this bump here, some time occurring before, and leading to hypothesis how this event could relate to the problem afterwards. Another use case we see at some of our users is the optimization of startup and change procedures. So startup procedures can refer, for example, refer to in energy to starting up power plants and ramping up the power consumption, but change procedures can, for example, refer to in continuous manufacturing, to switching from one grade to another grade. And those type of procedures are typically one critical point for process optimization. And as we see here in this example, there are some great change procedures kind of clustered in a way where it's where we're able to analyze with regards to other process data how the red ones under which conditions basically the red cluster leading to faster convergence occurred, and under which conditions the slower blue ones occurred. And as a third use case, it's about an important part of digital twins is using it for kind of what-if analysis. And one particular application is operation planning. So what we see here, this might not be so self-explanatory, is basically that you have a target variable, which is here on the y-axis, and you have three input variables here on these three plots of the x-axis. And you can think about this as a slider that you can shift, and that can also be controlled by some external sensor data, and basically you see how your target variable changes if the various inputs change in certain ways. Yeah, so for example, here in the first plot, you would see that if this parameter here increased, you would see that the target would increase in a nonlinear way too. Okay, so this basically also already brings me to my summary and conclusion. Digital twins are very much about analyzing lots of messy data. So actually they're analyzing much about analyzing data, and much of this data, especially in the context of industrial processes, is often messy and not easy to deal with. And this is important in various stages of a digital twin life cycle, starting with calibration, validation, decision-making, monitoring, and being able to understand and prepare historic process data can be and typically is a very time-consuming part of the work for building and also using digital twins. And so how interactive visual analytics can help there is that it can reduce costs and project durations of building digital twins. It can increase the plausibility by being able to much more deeply validate and also monitor digital twins, like making conclusions that in this condition the digital twin is behaving very well, but in certain conditions it's behaving not so well, and so that it might be optimized for certain conditions. And it can enable subject matter experts without deep background in data science to also use digital twins and the results of digital twins for their decision making. Okay, so thank you very much for your attention, and I'm very happy to discuss this with you now.
Thank you for this presentation, Harald, and for highlighting what you can actually get out of multi-variable time series data. I'm always quite impressed what you can do with the right tools. Markus has a question right away.
Yeah, I think it's obvious that I have a question because you were talking about solar power plants. I have a really simple question, because you're coming more from the software developing side, where we have another partner. You said in one slide that you need the domain knowledge of the experts. How much domain knowledge do you think you need to set up your system, and how much do you need to get added value out of your system? Because you said, okay, 80% of the time is just going into data cleansing and stuff like this. I assume that you don't need a lot of domain knowledge there, but how much domain knowledge do you really need to get an added value for the customer afterwards? So is it more 80-20 or 20-80, or when does the domain knowledge comes into your system?
It's a good question. I think to some degree the answer would be it depends.
Of course, but just for your gut feeling.
So what I can only be, so you're right, I'm coming from the software engineering part, but we have been, of course, collaborating with partners from industry and energy sector for quite some while. And what we see again and again is that you actually, for many questions, you do need deep domain knowledge. Yeah, I think it's kind of course there are some parts which you probably don't need domain knowledge. Like, okay, you will be able to identify some outlying data points, or you will also recognize some missing parts of your time series data also without deep domain knowledge. But actually, this is mostly not where the value is. So for example, coming to this example of this building this physically plausible digital twin of the power plant, basically this customer is stressing a lot the fact that you do need the role of this physical plausibility. Yeah? And this physical plausibility is something that you cannot purely infer from the data, yeah? To some degree, because as I said, the data will typically not cover all, the historic data will not cover all situations that can occur in your power plant. Yeah? And so basically, in order to say what's plausible or not, you need to have some knowledge in this domain, yeah. Because frankly speaking, I could look at some I personally could look at some correlation, being no energy expert myself, and couldn't say if this is plausible or not, yeah. And I think
yeah, that answers already a little bit my question. It's hard to come up with a certain number, but I think you have the same lessons learned as I have, although I'm coming from a different side, because I had the question 2 years ago, do I hire a thermal power plant engineer from Russia, or do I hire a data analyst from somewhere else in the world? And I decided for the power plant engineer, and I think it was the correct decision. Because if you don't have the domain knowledge, it's almost impossible to set up a digital twin that gives additional value. And it's easier, I think, to invest additionally in the data science part than or let's say to invest externally in the data science part than to invest or to buy on the external market the domain knowledge. So you have the same impression that I have.
And I think, so this is basically also some feedback that we get from many of our customers, that they think it's kind of easier to bring their domain experts with some deep background in their specific processes and conditions a bit closer to advanced analytics than to train people coming from the purely data-driven data science part, than to fully understand all of their processes. Yeah, of course, it depends what you actually want to do. If you want to build some deep artificial intelligence, deep neural networks and things like that, the story might be different. But there are many articles saying that much of the benefit that you can get from your data, and I'm not only referring to digital twins here, but rather data maybe on a bit broad scale, is much lower or a much lower hanging fruit than building the most sophisticated models possible. Yeah, and I think also this kind of mental pyramid that basically matches at the bottom, which you can basically achieve maybe by just looking at the time series with some kind of background knowledge, yeah, is where much of the benefit is. And of course, there will be applications where you need things like very sophisticated models, which you will need data science background. But I would say this is the 20% and not the 80%.
Thanks.
I know you also raised your hand sometime in between.
Yeah, it was mostly to go in that same direction. I think the subject matter expertise is much more complex and hard to get than the data science. Even there is a huge buzz around data science, but in the end, it's something that is being formalized, and you have thousands of books and stuff like that that you can quite more easily get than the subject matter expertise for each of the processes individually. My understanding that each power plant is going to be unique combination of different, each capability going to use a different brand of machine and so on like that. So each power plant is unique, and there is no generic knowledge about it. So it needs like 20 years of hands-on experience on that specific power plant to get that specific domain knowledge. So that's not something that you can easily acquire elsewhere. So data science expertise overall, and with all the tools that like the one that Visplore is developing, is a lot of tools that can make that expertise much more easily available. So yeah, it's the same thing that we're seeing. It's much easier to train subject matter experts into data science than the opposite. So just to support that comment.
Thanks. Sam, Harald, you like in the beginning you said that you told us about these digital twin use cases, but of course your tool can also be used for like various offline applications in data analysis and data science. So what's your experience? Do like customers, once they do the analysis of the data, they see that there are some patterns in there, or they draw some conclusions from the data on the processes? Is there like a need for automating these things? Like, do they start with data analysis and then want to build a digital twin?
Sometimes. In many cases, it's actually the opposite, that the management says we need to do digitalization and AI, and everything needs to be automated. And in the way down to the bottom, which I tried also to kind of put some spotlight on, and also looking at some real data, people discover that in some cases they are not even ready yet for the very ambitious goal towards automation, because basically there is much groundwork to be done. Yeah, and they need to start with things like installing the right sensors and I think one of the recent presentations was about engaging a data custodian to look at their data quality and things like that. Yeah, and then this is where the practice is, and then having some data engineering of integrating 5 different data sources and things like that. And then they realize how much they can gain actually by looking at correlations and comparing time periods and looking at things with some kind of background knowledge and intuition. And this is actually the part where Visplore comes in. And then once they learn this and they are in a state of having really a good knowledge of this, then it actually makes it much easier to come back to the long-term goal of automatization by getting the right models, selecting the right data, selecting the right features, being sure to have installed the right sensors that can actually make a real prediction, to have included the domain knowledge. Making sure that this basically works. Yeah, and So this is the answer, basically. It typically starts with an automatization goal or vision by the management, and then it goes down to reality, and then it goes step by step back again to automatization in the AI.
Mm-hmm. Well, thank you. But this actually matches like part of our experience. There's this big digital twin buzzword, and once you start looking really closely, you realize that there's a huge gap in between like the state of digitalization, optimization, where like big part of the industry are, and what we at the university think that you could actually do if you just had the right kind of sensors and the right kind of algorithms. All right. Are there some more questions to Harald? Well done, perfect. This has really been an extraordinary project presentation session. We've seen such a wide array of different approaches to digital twins. Some very data-focused approaches, which to me were like I think the most interesting ones. This approach by KMD with the clustering is also really innovative. I'm really glad that I heard about it and got this inspiration. So thank you for that.